Okay, next, enough about timer. The next thing is we're going to go into chapter 9.
Huh? This is 12 or 9, sir.
What's that? Chapter 9, chapter 9.
Then just now that one is
Chapter 8. Timer is chapter 8. Serial communication is chapter 9. ADC is chapter 12. Okay, we're going to see serial communication. Now this serial communication is one of the very, very important thing because whenever we're dealing with the microcontroller, definitely whenever you want to do a project, you need to interface it with another device, another electronic device, for example. Of course, you have already seen how to interface to binary devices such as switches, LEDs, 7-segment, those kind of output devices you have seen. Now, it can also be used to connect to other microcontrollers or any other devices as well. So one of the most easiest serial communication is actually this one, the USART. Of course, there are many actually here. So why do we actually choose serial communication? Before you all were born, they were using the parallel input-output pins. Have you seen the printer? I don't know whether you have seen or not. So that's why I said before you were born. Those days printer have a very large cable and a very thick cable, and it's called a parallel input-output pins. It's obsolete long time ago. So the thing with the parallel is the data transfer is fast, but unfortunately, as your data grows, your cable also grows because it assigns one wire to one bit. Just imagine you want to send 64 bit, you have 64, they'll come like TNT cable. And if the technology evolves, it cannot keep increasing. And the problem is, cables are expensive one, and also can only be used to transfer data for short distance. So because of a lot of shortcoming, serial communication, it was there, but it is still here now. But of course, serial communication has been overtaken by USB, so many other very fast communications. But serial communication is one of the most easiest and basic fundamentals of communication that you can have. So for those EE students, we will be doing this hands-on in next semester, or whenever you take the lab. So many applications do not need that high data rate. Of course, now you need high data rate, but serial communication can also work as fast, quite fast, sufficient. So the types of serial communications that are available is one is USART, which is universal, synchronous, asynchronous, receiver and transceiver. This is one of, it uses two signal pins, transmit and receive, and use the third one, ground. So whenever you want to connect two devices together, the transmit pin, usually the transmit pin and the receive pin in the microcontroller is port C pin number 6 and 7. It has, you can see in the data sheet, it put the RC2/RX and then TX. RX means receive, TX means transmit. So you have two pins, and you have another device also has two pins. The transmit one should go to the receive, you should cross wire it. Simple communication, right? You should cross wire it. The transmit should be connected to the receive, and this side receive should be connected to the transmit. So you just cross wire it, and both should have the same ground. It's a very simple hardware connection, but then whatever data you can actually transfer through these two lines. So you can see that later in your FYP, if you want to communicate with PC, you can use USART. Then you may ask, why can't we use USB? Yes, you can. But USB, you need to understand how it actually works. It's not as simple as you think it is. You need to have a lot of header files, you need to have the driver, so many things associated with it. No doubt, it will definitely be way, way faster. Last time I did with PIC18, during my master's time, I actually did the driver for microcontroller. Yes, it actually managed to transmit the data fast. But once I just load the USB program only inside, the full RAM becomes full. The whole program memory became full. I cannot write other program. The consumes a lot of space. For this one, it's very, very simple. Then you have SPI, synchronous. All this SPI, I2C, CAN and also LIN. Most of the time we deal with SPI, I2C and also CAN. These three are very, very prominently used in the industry. SPI, you know where is it used? Your SD card. Your SD card communicates with the electronic device, camcorder or whatever. It uses this type of communication. I2C, inter-integrated circuit. Where can you find this kind of communication? Huh? Sasi, where? Say something. PIC. PIC, yeah. Not inside PIC. This is inter-integrated circuit. That means you have integrated circuit is IC, and you have multiple ICs. They are connected together. So it cannot be inside the microcontroller. You can see a lot in electronic devices like your
chipset,
TVs,
motherboard,
chipsets and things like that. So they have a lot of ICs and they actually communicate among themselves. In a lot of electronic boards you can see they have this inter-integrated circuit. This is I2C. How do they communicate among themselves? And then you have the CAN bus, controller area network bus. Where can you find this? Mostly now, what? Come again?
Router.
Just because the network word is there, you're whacking, right?
This is control area network bus.
In automotive. In automotive, you can see controller area network bus. This means you have a lot of controllers. All these controllers, they are actually connected by a network. Inside car, you can see this CAN bus is in car. Take and check on the thing inside lah. Modern cars, one microcontroller for your fuel injection, the ratio, another one for. But all these microcontrollers, they are actually connected together. There's one ECU which actually controls another controller which controls all the different parts of the car. So this is very useful. So if you know this one, of course, as a student you should know later on. If you know these three things, you'll be very much demanded in industry. This one you learn in advanced micro P. So if now it's in never. So lean enterprises won't be covered. Anyway, all these things won't be covered. So just for information I'm telling you so that you know what kind of technologies that you have. So this USART, we are focusing on the USART. This USART is also known as RS232. Sometimes whenever you go to shop, you want to get the port, you ask, can I have a RS232 port or the terminal RS2? Someone say, can you please connect this cable to the RS232? Huh? Back. So don't say, give the reaction. RS232 is actually is for the USART connection. And we have this standard developed by the Electronic Industry Association, called EEEB. They have a standard for everything. So if you see all around the world you go, this is actually standardized. USART communication is standardized. So sometimes you see like how Wi-Fi, you have IEEE standard, right? You can see in the specification IEEE 802.11G. You see that specifications, you know what is that, how that particular connection actually communicates. You know what are the frequency, what is the capacity, like everything, all those are actually being standardized around the world. So you don't have Malaysian standard, you don't have US standard, it's actually standardized around the world. So this one, as I mentioned, is known as RS232. So there are 4 aspects to the EIA standard 232, which is very, very, very important. Which I do not know why it has to be important, but it is very, very important. It has electrical specification, functional aspects, mechanical specification, and procedural specification. It makes no sense to you, but I do not know why is it important. But it is important. Let me just explain about the electrical specifications and then I'll focus on the mechanical so that you know how it looks like. The rest is actually, you won't be even bothered to know. So the electrical specification is, one is how fast are the data rates. Now these are the data rates available. Now most commonly used data rate is 9600 by default. Even though if you go on a PC, if you check your terminal, if you still have, or if you download a software to have a virtual serial or things like that, you can see that the default speed is actually 9,600 kilobits per second. So that means that shows how fast it transfers. Per second is actually transferring 9,600 kilobits per second. Bits per second. So they also are not actually 9,600, it's different, sorry. It's known as the baud rate. All these values are known as the baud rate. There are some calculation to actually get the baud rate. Yeah, it's actually 9,600 bits per second. So whenever, you see this is communication between two devices. So whenever you set the data rate speed, both data rate speed must be the same. You cannot be transferring one very slow and one very fast. What happens if you send one slow and one fast?
It won't be.
Since it's not synchronized speed like that, you may have loss of data. It's likewise, when you send something too fast, but you're capturing it slow, definitely have loss of data. So we want to make the speed synchronized. If you choose here 9,600, here also should be 9,600. Simple concept. Take note that the voltage assignments are actually different. The voltage between -3 to -25 is actually considered as logic 1. Voltage between 3 volts to 25 volts are considered logic 0. Now, just now I say if you take two microcontrollers and if you connect the C6 and C7 pin by twisting the wire, cross wire and connect to the other PIC, yes, you can straight away communicate, no problem. Whenever it's communicating in that way, it's only communicating from 0 to 1 volt only. It's not communicating this range. This one only when you're communicating to a device which has RS232 port, for example computer, your laptop doesn't have that, old laptops have, or desktop PC have that, the serial port. Serial port looks like this. Serial port looks like on. Out of all these pins, you only will be using for simple communication and it works well. You only use transmit, receive and also ground. 3 wires is enough. Even though you see so many pins, if you cut the wire and see only got 3 wires connected. So only when you want to connect from microcontroller operates on a 0 to 1 logic, right? If you want to communicate from one microcontroller to another microcontroller straight away, no problem. It's compatible. 0 to 1, 0 to 1. Okay, no problem, you can communicate. But let's say you want to communicate, you want to send data from a microcontroller to your computer. Suddenly you want to do some data analyzer. You actually develop one GUI, graphical user interface using VB, and then you want to capture the data from the sensor. The sensor is connected to the microcontroller, and the microcontroller each time it captures. Let's say you write an intra program. Every 1 second, capture the input from the sensor and send it to the computer. Now you need to connect from the microcontroller to the computer. Now there's a difference in logic. Computer is not working on 0 to 1 volt. It has a different voltage level. The port at the computer, this port here, operates on that voltage. Just now you see. And whatever voltage that you're sending logic 1, logic 0, it will be in that voltage range. So from microcontroller to here, it needs to do the voltage translation. Right? It needs to actually do the voltage translation. So therefore, you have ICs like Maxim 232. What that IC will do is it will actually take the data and it will convert into that voltage level. When the computer receives it, it will be able to get it as 1 and 0. So that is the translation is only required when you're communicating from a microcontroller to another device which has this one. Is it okay? Okay or okay? So how is the data format being sent? question up to this point? Or you all refuse to ask question? Final, no one. This is actually why I'm still telling you, because it is very, very useful, and you may want to use for EE students. Definitely will be using it in lab. For FIP you will use it, and to set it up is so simple. It is so simple to set it up. So that easy, but it's very useful. Send data, you can actually monitor. So how the data format is? So the data is transmitted character by character. Each character is preceded by a start bit, followed by 7 to 9 data bits. Now usually this one, the data bits, serial communication allows you to send 7 to 9 bits at one time. So you can also configure that. If you see in your properties of your UART, you can see the baud rate by default will be 9600, and then the bit rate also, the data size also will be 8. But you can also set it to be other. But there will be some application when you need to send more than that. I did that during my masters also, because I did one custom algorithm to send a custom data, do a custom task. So I used the baud rate, but I didn't follow I used 9. Then I captured. So there will be a lot of thinking required when you capture something more than 8 in microcontroller, because each time you want to store, you store in 8s, right? So when you have more than that, there's a different way you need to store. That one is a long story. And terminated by 1 or 2 stops bit. So always remember that the data will be here. It will be preceded by a start bit, and you have a stop bit. Now why we need this start and stop bit? This is so that the receiving side will know the start bit always will give logic 0. When you have logic 0, take note that the stop bit always logic 1. So after logic 1, the start bit will give logic 0. The first logic 0 that it receives, it actually acknowledges it as, okay, now start. After the first one, depend on how you set. If you set as 8-bit, the subsequent 8-bit is actually captured as the data. And then you should also have the stop bit to indicate that yes, this is end of this character. And then again go to start. So each time it can know each character is coming and will be able to capture. Is it okay? So start bit always 1, stop bit you have option either 1 or 2, but the logic is always 1. Is it okay? It's quite relatively simple, right? So let's see an example. Sketch the output of the letter K. Sometimes you want to send some character through the USART. When it is transmitted using the format of 1 start bit, 8 data bits, and 1 stop bit. So start bit is okay. Start bit. Now, okay, another thing is you need to know that letters are represented in ASCII code. K is actually hex 4B. If you translate it into, always take note that ASCII is only 7 bits. But the most significant bit always will be 0. So it will be 0, 1, 0, 0. B is 1, 0, 1, 1. Even though if they ask to do such a question, they will actually give the ASCII code, so don't have to worry. But later on, if you need to do on some projects and things like that, if you want to know what is the ASCII code, you can refer to the ASCII table. You can find out what is the ASCII code. So that means this is actually the data for the letter capital K. So you need to send it using USART format. So it says 1 start bit and 1 stop bit. So always remember, start bit is always 0. And then, how do you start this? Take note that whenever you want to send, it will start to send from the least significant bit first. And then, so that's why it will count 1, 1, 1, 0, 1, 0, 0, 1, 0. So do you see it's reverse? Then after the last one, stop bit always logic 1. Is it okay? One of the final years came, I can't remember last semester or before that, came on this question. Very simple. Now you may ask why there's another output. Now the output waveform at the interface, you just have to toggle it only, it's the other way around. So this is the output waveform at the microcontroller, gives the microcontroller this output. The output waveform at the EIA at the port interface actually comes in this format. It comes in reverse. So with that, finish chapter 9. Yeah, wow. Chapter 9 is really wow. All this. So actually that's why I said, can you stop the recording?